On this page, I'm going to calculate the slope and intercept for a least squares regression line. I'll do it for this data set where some boys' heights were measured at different ages. As you can see, age is the x variable and height is the y. And it's believed that the height depends on the age of the boy. Now, this is bivariate data, which means that the data was recorded in pairs. Bi meaning two, so there's two variables, x and y. And so this pair here means that a 2-year-old was measured to be 36 inches. A 5-year-old here was measured to be 44 inches. A 7-year-old was 49 inches. And then we have a 12-year-old being 59 inches tall. Those are our 4 readings that were made. Now we want to plot them. Here is the 2-year-old. This is the 5-year-old. 7-year-old and the 12-year-old. Okay, we want to find the best fit line, not just by eye, but the statistically best fit line. So what we'll do is we'll actually transfer our data to a table. We'll need x, y, and we'll need x squared. We don't actually need y squared in our formulas, but we do need xy. Okay, let's write down the data pairs next to each other. The 2-year-old was 36 inches. The 5-year-old was 44 inches. 7-year-old, 49 inches, and the 12-year-old, 59 inches. Okay, we'll just want to square those x's now. So 2 squared is 4, 5 squared is 25, 7 squared would be 49, and 12 squared is 144. I'm going to skip the y squareds. We do actually use those when we're calculating the correlation coefficient, but in this particular problem we just need the least squares line, so I'll leave that off for now. 2 times 36 though makes 72. 5 times 44 is 220. 7 times 49 is 343. And 12 times 59 makes 708. Okay, now we want to find our sums. Okay, so 2 plus 5 plus 7 plus 12 makes 26. We want this to be a 26. Our sum of y is 188. Okay. Then we should sum our x squareds. Okay, it makes 222. Then let's sum our xy column. $13.43. All right. Now we're going to use the slope formula first. We have to do that one first because the y-intercept formula actually includes the slope. So if you don't know the slope, then you can't use this formula. So let's start with the slope. So we'll do m equals n, which is going to be 4, okay, times the sum of x, y, 1343. Then we'll subtract the sum of x, which is 26, times the sum of y, which is 188. And I'm just going off each of these expressions here. N is the number of data pairs that you have. Okay, so there's 4 coordinate pairs. 1343 is the sum of x, y, which I got from right here. 26 is the sum of x, which I had gotten from here, and 188 is the sum of y, which was taken from this column here. Then we just have to divide by n again, times the sum of x squared minus the sum of x with a square on the outside of the parentheses. I get that the slope is 2.28. Okay, now let's find the b-intercept. For that, we want the formula here, the sum of y over n. So that's going to be 188 over 4 minus our slope, which is 2.28. And you may want to keep just an extra decimal place in there. It'll help us to not be off by rounding in our b. Okay, then we'll do that times the sum of x, 26 over n. Okay. So our b is 32.16. Okay, now that we have the m and the b, we can write the regression equation. It will be y of x equals 2.28x plus 32.16. Now let's interpret the meaning of the slope and intercept. So our slope value is 2.28. What does it mean in the context of the problem? And so you want to talk about the rate of change here between the variables involved. So I'll put for each year that passes since birth, a boy's height tends to increase. By 2.28 inches. So we're relating the change in one variable to the change in the other variable. That's the meaning of the slope. Okay, now let's talk about the intercept. The intercept says 32.16. What does it mean, though, in the context of this problem? So we could say at birth, at time x equals 0, the initial height of a boy tends to be 32.16 inches. On this page, we'll use our linear regression equation to make predictions about the heights of boys of different ages. Now we already have 4 data points plotted here. And there is some best fit line that goes through that. The equation we came up with on the other page was y hat equals 2.28x plus 32.16. Okay, so let's use it to predict the height of a 7-year-old boy. We want to let x equal 7. And then plug in a 7. Okay, I get 48.12 inches. Keep in mind that we didn't actually collect data on a 7-year-old who was 48.12 inches. We actually collected data on one that was 7 years old but 49 inches. Pretty close. But the prediction is based on the green line, not the actual data. It's a mathematical model that tells us what height we would expect a boy to be if it was 7 years old. Now, is it interpolation or extrapolation? Let's look at the definitions. Interpolation is predicting y hat values for x's that are between the observed x data values. So are we doing that here or not? Well, we collected data on a 2-year-old and a 5-year-old, a 7-year-old, and a 12-year-old. So those represent the range of our collected data. Okay? Now, a 7-year-old is within those boundaries. And for that reason, this is called interpolation. Simply because the 7 is between 2 and 12, the extremes of the ages that we had collected. But now, let's look at what extrapolation means then. Extrapolation means predicting y hat values for x's that are beyond the observed data values. And extrapolation is considered in the mathematics of statistics to be not as reliable as interpolation. And we'll see why with these 2 extreme examples. So, first of all, could we use the model to predict the height of a newborn boy? Would it be interpolation or extrapolation? Well, you want to let x equal 0. Okay, and plug in 0 years into the equation. And of course, here we just get 32.16 inches. Okay. Now, where does that actually happen on the graph? Over here. That is y hat of 0. Is it interpolation or extrapolation? Well, we said before, it's interpolation if you're between the 2 and 12. And here, since we're actually beyond the data values that we collected, we didn't collect any data on 0-year-olds or 1-year-old even. So that is going to actually be extrapolation. Okay. Now it's conceivable that 32 inches might be a good prediction of the height of a newborn boy. But what about this next example? It says, find the height of a 25-year-old using the model. If x is 25, you'd plug in a 25 here. And I get 89.16. So how many feet is that? Divide by 12 inches in a foot. It's 7.4 feet. So is that a realistic prediction of the height of a 25-year-old? The answer is, of course, no. And the reason is that we didn't really collect data for 25-year-olds. We only collected it from 2 to 12-year-olds. And so there's some kind of phenomenon going on with the growth of a person here that makes it not linear at all ages. Okay. So this is an example where extrapolation would be the wrong thing to do. You'd want to actually collect data on 25-year-old and use that. So what is the model that would be best for this situation? Well, if we were to extend the graph, what we may find is that that intercept might be pretty close. And it might be linear for a while, but in all reality, over time, we see a plateau and a sort of leveling out of the heights where it reaches an upper limit that, people will stop growing at. All right, so anything to the right of 12 would be considered extrapolation until we get the data that we need in order to make a better curve here. And in truth, the height of a person throughout their lifetime is not linear throughout the entire lifetime. But we used just this region here. And for that reason, a linear model actually works well.